Hello everyone and welcome to another video. So today I'd like to continue our discussion on multivariable calculus. If you've been following along, you know in the past we've discussed line integrals, double integrals. So why don't we continue that discussion to the next logical progression, which is now surface integrals. So in order to talk about surface integrals, I think we better refresh our memory on what we mean by surfaces. So remember, in our immediately preceding video, we talked about how to parameterize surfaces and how to do things like calculating their normal vectors at any given point. So just like I said, to quickly refresh your memory about that, I've just drawn a quick picture. So remember, the idea is we have some surface S which might live in XYZ space, and the idea was we were able to parameterize this surface by looking at some region R in a UV plane, and then for any location R, you know, here's a U and a V, right? We had some parameterization function which basically allowed us to map that location of U and V to a three-dimensional point in space XYZ, right? So that was our parameterization function, which we sometimes refer to as R bar, right? Now, the idea now is, okay, now that we're able to define this surface, right, by basically moving U and V around this region R in the UV plane, and then running all of these points through our parameterization function, we will describe this surface S in XYZ space, right? That was the idea. Now, what we want to do now with the surface integral is, okay, this is great that we have this entire surface, but now, what if we have some parameter which might vary over this surface? So like, for example, right here, maybe there's a temperature at the surface here. And then there's a different temperature over here, and a different temperature over here, and a different temperature over here, right? So there are different temperatures or some other scalar quantity defined over this surface, right? So the idea now with a surface integral is we want to integrate all of these temperatures or densities or whatever this function f is. We're going to call these purple points, we have a function f, lowercase f, which defines this function, right? So in other words, let's consider just some scalar function, right? It might be a function of multiple inputs, but it just has one output. Namely, you tell me where you are in space, in like XYZ space or whatever, and this function will tell me what the temperature is, right? So this is the picture that goes along with it, right? So now in this context, if we have this scalar function and we have this surface, we can now define a surface integral, right? So in this case where f is a scalar function, we're going to define our surface integral to just be this, right? So again, this is the conceptual way to think about just writing it. It's basically a double integral over the surface of the function value times some small elemental area of that surface, right? f dot ds, right? So, like we talked about in the past, this is a nice way to conceptually think about it, right? All you're doing is you're taking the function value, multiplying by the little bit of area, right? Which is basically all we were doing with double integrals. Now, this is nice to think about, but the way we are actually going to practically implement this calculation is down here, okay? So again, this should now hopefully make sense what we're talking about. What this is saying is we're going to evaluate that function f, right, at the location of our parameterization uv, right? So again, in this picture, this is literally this large fat purple point right there, right? The function value at this location, right? And then I have to multiply it by this thing. And again, we talked about what this n vector was in our previous video. This n vector was basically the cross product of the partial derivative of your parameterization with respect to u cross with the partial derivative of your parameterization cross with v. And what we saw last time was what that quantity gave us, right? This vector n is basically a surface normal vector like this, right? Right? So this gave us the normal vector, and this was not unit length, right? This is literally just a cross product, right? So what this is this vector, which is normal to the surface at this point of interest. That's what this term is, and then we just take its magnitude, right? So this is the practical way that we will go about computing this surface integral, is we basically just march our way around this entire surface by looking at the magnitude of the normal vector times the function evaluated at that location, and then we are actually going to do a double integral over the UV plane down below, all right? So again, This is the conceptual way of thinking about the surface integral of what we're doing. We're just basically adding up the function values around the surface, but this is the equation of how we're going to go ahead and implement this, right? Okay, so maybe I think the easiest thing to do then is let's jump into an example and see how this works. All right, so let's look at an example of how a surface integral can be used to compute the surface area of a surface. So let's consider that same hemisphere example that we looked at in our previous video. So this was the parameterization and this was our domain in the UV plane. And again, remember, this basically describes half of a perfect sphere of radius A, the upper half of it. And again, here's my horrible drawing of it. Here's an actual screenshot of what it looks like in Mathematica. Again, this is the exact same example we used in our previous video. So again, here's the surface. Here's our domain of integration in the UV plane. And now what we want to do is let's try to integrate some quantity over this surface S. Now, the quantity we're going to look at is, let's just use a scalar function of f equals 1 or equals unity. The reason we're going to do this is we're going to see that this is going to actually allow us to compute the surface area of that surface S, okay? So if f is equal to 1, basically what the surface integral does for us, the surface integral is equal to the surface area, okay? So again, this was the idea. We just need to now integrate this function f, which in this case is just 1, over the entire surface. And then here's the practical way we're going to do this, right? So we have to do a couple of things. We have to compute, most importantly, in this case, we need this normal vector, okay? So again, we said the normal vector, in order to get that, we need to take the partial of the parameterization with respect to u, and then the partial with respect to v. So again, I've just gone ahead and done that, and as you can see, this term right here, all I did was take our parameterization here and take the derivative of each term with respect to u. This is what you end up with. Same thing down here, rv is the partial of this parameterization with respect to v, and this is what you should end up with, okay? And then lastly, to get the surface normal vector n, you just need to take the cross product of the two of these things. And again, take my word for it, but if you do the boring algebra, this is what you end up with, right? Now, in our expression here, we've got the surface normal, but actually what we care about is, as you can see, it's a vector, right? It's a 3-element vector. We actually want the magnitude of this vector. So take this part squared plus this part squared plus this part squared, square root it. And what's fascinating about this is the magnitude just turns into this quantity. It's just a squared times square root of sine squared u. So now we're pretty much free to plug it into this expression down here, okay? So let's go ahead and do that again. So our surface area is equal to now, again, our double integral of f of r of u. So in our case, f is super easy. So actually, it doesn't even matter what our parameterization is or what values of u and v we have. This is just a 1, right? So this first term is just 1 times this thing, which is the norm of the surface normal, which is we just got here. So it's a squared square root of sine u squared, right? And then du dv. And now we can see, what does u run between? U runs between 0 and pi over 2. And then v runs between 0 and 2 pi. So as you can see, we basically just have a pretty much run-of-the-mill double integral at this point. So just turn the crank, do this double integral, and I think what you end up with is, if you run this through Mathematica or any other tool, or just calculated by hand, let's do this 2 steps. I think what this turns out to is, let's do the inner integral first. So we're going to leave this. So the inner integral between here and here, right? This turns into, I think it's just a squared. Okay, and then again, you just do this integral with respect to v, and this just comes out to 2 pi a squared. So here's our surface area expression. And as you can see, this agrees with pretty much the well-known formula for the surface area of an entire sphere, right, is 4 pi a squared, right, or 4 pi times the radius squared. So since we only have half of a sphere here, we just get half the surface area, right? So the other thing to maybe mention is to think about is, this is sort of getting us the, if you want to think about it, one-sided surface area, right? It's not the entire wetted area. It's not the outside skin plus the inside skin, right? It's just the surface area of the outside or the inside. Both of them are the same here because this thing has no thickness, right? But again, just think about that, that what we're getting here is sort of the one-sided surface area, not the total wetted area of this surface S. right? Okay, so great, that was pretty easy. Let's look at an example of what happens if we change our f ever so slightly. All right, so let's modify this example. Instead of surface area, let's see how we can use the surface integrals to calculate things like, I don't know, maybe how about total mass of a surface. So again, let's consider the exact same surface, the exact same parameterization. The only thing that we want to now change here is this f. Instead of making this 1, let's make this kind of maybe like an interesting function. Let's say we know the density of this surface S. Let's pretend S is made out of some funny non-homogeneous material and we want to get the mass of it. So what if we know the density distribution at any given UV location, right? So this is in units of, say, like kilograms per meter squared. So it's sort of like this, the total mass normalized by the surface area. So it's like a specific sort of density with respect to surface area. So this gives us some density distribution, and I don't know, let's make up this distribution here. How about something like 3u plus v, okay? So now what we're doing is this surface area is not actually getting, or the surface integral, now what we're doing is we are going to integrate up this mass distribution over the entire surface. So this should give us, hopefully, total mass of this object. Right? Now, the thing that makes this interesting is that the density, like we said, it's not uniform. This thing is non-homogeneous. Some parts of the surface are denser than others. And in fact, maybe the easiest way to go about this is let's go over to Mathematica and I'll show you what this function looks like in relationship to the surface. And that might help us wrap our heads around the physical picture of what's going on. All right, so here we are. I just made a little Mathematica animation to help us understand what the situation looks like. So what I've done over here is I've plotted basically that function of the density. So again, remember the density, it was what? It's 3u plus v. So I think everyone understands that that's basically just a plane in three-dimensional space. And as you can see, here's what this plane looks like, right? So as u varies between 0 and pi over 2, and v varies between 0 and 2 pi, this is what it looks like. So apparently down here, when u and v are 0, the density is 0. So I guess at that particular location, right, this thing has a super duper thin wall, if you want to think about it. Whereas way up here, when u is high and v is high, the object is super dense, right? Now, I've also plotted that same representation sort of from like a top-down view using a color map. So again, you can kind of see the numbers. So blue down here at low U and low V, these are not very dense, super light areas of the object. But as you increase in this direction, the object gets more and more dense. So again, this is very easy to understand what it looks like in the UV plane. But now the question is once we map these UV locations to XYZ locations through our surface parameterization, where are those locations actually on the hemisphere, on the actual surface? So as you can see right here, when U and V are down here at 0, that actually means on the object, we're at the very top of the hemisphere. So apparently at the very top, we have a really, really thin wall, if you want to think about that. And what we can do is, tell you what, actually, let me open up these controls a little bit, and we can kind of move these numbers around. So as U increases, right, we can see the density is increasing. So I'm trying to use that little green dot to show you where we are. So now, you know, I don't know, let's move it over here to, I don't know, like this location or something like that, right? So now you can see at this U and V location, the density has increased, and apparently that corresponds to this area of the actual surface. So again, you can kind of play around with this, and as you can see, depending on where you're located on the object, right, or on the surface, the density of this sheet metal object is changing, right? So as you can see, this is a somewhat complicated problem in the sense that since the density is such a complicated function and you combine that with the geometry that's also fairly complicated, how can we get the total mass of this surface S over here when it has this kind of odd varying density? So let's go back to the board and actually compute the surface integral, because that's how we're going to compute it. All right, so let's go through and see what changes. So again, this is the same from the previous example, and you can see that this is the same, right? The surface normal vector doesn't change because we're dealing with the exact same surface, right? And therefore, the magnitude of that surface normal doesn't change either. Now, this is the only spot where we have to make a change. So earlier, our function f was really simple, it was just 1. But now, this function f evaluated at RUV is actually this, right? And the nice thing is we already have the function in UV space, right? So since we described this here, this is basically our function at R of UV, right? So what we plug in here is now just 3u plus v, and then we have to multiply by a squared times square root of sine squared u, which was, again, the magnitude of the surface normal. So again, I think this just changes ever so slightly, so this inner integral now gets a little bit more complicated. Did I actually define that? Term 1, yeah, I think this is now 25 times 3 plus v. Okay, and then you integrate this guy again, and now we don't have surface area. That's not what we're computing. We are getting the total volume, or total mass, is going to be, by the time you do this integral, I think this comes out to 150 pi plus 50 pi squared, or if you want that as a number, it's about 964.719 kilograms. Great. So as you can see, this is actually pretty darn helpful. You can use this surface integral of a scalar function to do things we saw, like computing surface area. You can get total mass. You could get centers of gravity if you want. So there's a lot of different things you could do using a surface integral of a scalar function. Okay, so with that, maybe let's talk about what about surface integrals of vector functions. All right, so now let's consider surface integrals of vector functions or vector fields. So now the only difference that we want to make is now the function f that we're considering, it's not a scalar function anymore, it's a vector function, meaning that its output is a 3-element vector. So it's like a vector field, right? So the picture that goes along with this, right, again, is we have the exact same idea, right? All these things are the same. The surface is the same. We just got a surface S. We've got a region R in the UV plane. We've got a parameterization, all that kind of stuff, blah, blah, blah. It's the exact same thing, except now what we're considering is that this function f, it actually defines like a vector field, right? So here's f, right? And this could be doing different things. It could be pointing in different directions at different areas in space, right? Maybe this is like a flow field or something that you can think about it like a velocity field. If this is like fluid going around, fluid can be flowing in all these different directions. Our function f is describing how that fluid flows at any given location, right? So now within this context, we want to be talking about what does it mean to have a surface integral of that vector function over the surface S, right? So again, the easy way to think about this is just like conceptually what we're talking about is we now want to take the dot product of the vector function f with some sort of surface normal times an area of that surface, right? So you can kind of think about a small little chunk, right, here, right? This is like, and this thing has some kind of normal vector, which we're going to call, let's maybe make it a unit vector for now, like n, little n bar, right? And now we're going to dot product the flow, so to speak, that is going through this spot, right? So here's f, dotted with the normal vector and then multiplied by the area, right? Which is sort of what we've written over here, right? So this is the idea of a surface integral of a vector function. It's basically taking like a dot product. It's similar how when we were looking at how line integrals can be used to calculate the work of moving a particle through a some force field. This is almost as similar in the sense that we're adding up all of the flow and the dot product, the components of flow that are normal to the surface at any given location, right? So that's, again, this is sort of the conceptual idea of what a surface integral is. We're trying to capture, so to speak, the flux of this vector field that is going through the surface S, right? And again, this is the nice idea of how to calculate it, right? Where you just take the vector function dotted with a unit normal vector and multiply by some elemental area, right? But in practice, the way we're going to do this is we are going to parameterize this surface S just like we've done before. And now here is a much better formulation of doing this vector or doing the surface integral. And again, this is very darn similar to what we saw earlier. This is now the vector function f, right? But we have to evaluate it along the parameterization that we're interested in. And now we dot product with it with the surface normal vector at any given location. And again, I will maybe call out the distinction that in this formulation of the surface integral, this is the non-normalized unit vector as opposed to what we were talking about over here, which was the unit normal vector. So again, down here, what we were talking about is, you know, this is probably something like this. It's going to point in the same direction, right? But that's all we're doing. Okay, and again, you can kind of see the bones of this. This is making sense, right? This is giving us the vector function at any given location, and then we're going to dot product it with the surface normal vector right here, and then we're just going to integrate over the entire region R down here in the UV plane, right? So that's the game plan. This is the handy dandy formula of how to do this. And again, we talked about how to get the surface normal vector just a while ago, so I don't think we're in too much trouble. We should just probably jump over to an example and see how this works. All right, so let's look at a concrete example of this and use the surface integral to calculate the flux flowing through a surface. So let's say that we've got a surface that's defined by this kind of set of constraints, right? So y is equal to x squared, and then x is free to go between 0 and 2, and z goes between 0 and 3. Now, this is actually the equation of basically, it looks like a parabolic sheet, and we'll look at that in a second. Now, we've got that surface in space, and now let's say we've also got a velocity flow field or a vector function, however you want to think about it, that's described by this, right? So at any given x, y, z location, here's the x component of the flow, here's the y component of the flow, and here's the z component of the flow, right? So now what we want to do is we want to compute the volumetric flow rate of this fluid field across this surface S, right? And again, instead of me just trying to talk about this or trying to sketch some horrible pictures on the board, let me show you a little movie animation I made in Mathematica which shows you this situation. So as you can see, the surface S is that parabolic sheet that we were talking about, and then all of the little arrows in that vector field are trying to represent this vector function at any given location. So as you can see, you can think about that vector field as describing the velocity of some fluid or something like that that's flowing across this sheet. And now I want to know how many cubic meters per second are flowing across this sheet in this vector field. So that's the game plan. That's the picture that goes along with it. So now let's go and do the calculations here using a surface integral. So the first thing we need to do is we need to parameterize that surface S, right? So here's one really simple parameterization. Just let x equals u, y equals u squared, and z equals v, and then let u and v run between these ranges. So here's our region R in the UV plane, and here's a parameterization of that surface S. So we're pretty much good to go. Now, we just need to calculate and turn the crank on our surface integral equation. So again, this was the idea of what we're doing. We're trying to take the vector field at any given location and dot it with basically a normal vector to the surface and increment and integrate over the entire area, right? So the way we're going to practically do that is with this equation over here, right? Which was basically the exact same equivalent, but just a lot easier to understand, and we can actually physically compute these quantities. So let's first start with the unit normal vector. It's the exact same thing like we did earlier. It's just our parameterization is different. So in this case, RU, I just take the partial of this with respect to u. I get 1, 2u, and 0. Then get RV, take the derivative of this with respect to v, and you can see it's easily 0, 0, 1, right? As you can see here. And then the normal vector is just I take the cross product of these two. And again, maybe here's a good spot to mention that you could have gone RU crossed RV, or you could go RV crossed RU. Either way is fine. It's just going to give you a normal vector which is pointing in one direction or the exact opposite, which might have ramifications on the sign, the SIGN of your answer, as we're going to see down the road, okay? So just keep that in mind. We're going to choose RU crossed with RV for our formulation of the normal vector. So if you do that, just cross this vector with this vector, you get this vector, right? So great. We basically have this term done. Now let's focus our attention on this term, which is the vector function evaluated along our parameterization, right? So again, our vector function f, it's right over here, right? So again, I've just rewritten it right here. Here's our vector function. But if I want to evaluate it along our parameterization, we have to evaluate this where we said our parameterization is what? X equals u, y equals u squared, right? And z equals v. So anywhere you see an x, substitute u. Anywhere you see a y, substitute u squared. Anywhere you see a z, substitute v, right? So if you do that, here it is. So this is the expression f evaluated at our RUV. So that's the other object or the other vector we need in our surface integral equation. So now the integrand right here, it's just dot product the two things together, right? So take this thing right here, dot product it with the normal vector, which we had over here, and that gets you your integrand, which looks like this, right? And then all we have to do is now we're at double integral time. We know what the ranges of u and v are, right? According to our region here, it's a region. So this double integral easy. U goes from 0 to 2, V goes from 0 to 3, and you turn the crank, and wha-bam, you come out with a number of 192 meters cubed per second. And again, maybe let's stress this is positive 192 meters cubed per second. And again, the reason I'm pulling that up and hammering on that is, remember, we talked about earlier this normal vector characterization that we use. In fact, maybe now might be a good time to bring up another movie where let's also add on this surface normal vector to the picture of the surface and the flow field and all of that stuff, and we'll spin this around a couple times, and as you can see, that green arrow is this surface normal vector, and if you look at it, it looks like this particular parameterization, we happen to choose the direction of this normal vector, which seems to be for the most part along the surface aligned with the flow, right? So the dot product between the flow field and the normal vector is positive for most of the integration, not all of the integration, right? Some points you can see that the normal vector and the flow field are in sort of opposite directions. So in those locations, you're sort of accumulating negative flux, right? The flux is flowing sort of into the object, if you want to think about it that way. But for most of the object and most of that surface, it's flowing out along the same direction as the normal vector. So you get more positive flux than negative flux, and therefore your overall answer is a positive number. And again, the only difference here is if we had chosen a different normal vector, the sign would have been reversed. So again, when we're computing the surface integrals of vector function, you got to worry a little bit about the orientation of the surface in the sense of what direction is that normal vector, and that has ramifications on your answer, especially in situations where you may want to say take this surface integral and you over a complicated surface, and maybe you want to break it up into smaller integrals over smaller subsurfaces. You just want to make sure that when you stitch all of your answers back together, you did each one of those smaller integrations with a consistent normal vector so that you're getting basically the same signed fluxes being added up as you go through it in an appropriate fashion. So, with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, that really does help if you click on the subscribe button. And remember, the new videos come out every Monday, so I hope we'll join you, and we'll see everyone back at one of these future discussions, and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.